So now we're in part 3 of our walkthrough of case study ex47 code. And what we've looked at so far was looking at the Memoizer implementation. We looked at the implementation of generate random data. We looked at the implementation of StampedLockHashMap. And now we're going to kind of show how all the pieces fit together, and we'll run the solution. You get to see what the output is. So what I'm going to do now is I'm going to go ahead and run the program. It's going to take a while to run, so we'll just let it run in the background. And what we'll do while it's running is we'll take a look at the time test method, and you'll see how it takes in these different memoizers that are configured with different collections. We have SynchronizedHashMap, which uses a single lock. We have ConcurrentHashMap, which uses a lock per hash table bucket. And we have the StampedLockHashMap, which uses the cool features of StampedLock. So the Memoizer is going to be parameterized with the appropriate map, as well as the isPrime method that we get from the prime utility class. As you can see here, all this simply does is it does a primality check on the prime candidate using a brute force algorithm that's intentionally designed to burn lots of CPU time. I've covered this before, so I won't spend a lot of time on it, but basically it just computes whether or not a value is prime. If the value is not prime, it returns the smallest factor. Otherwise, it returns 0. So that's what isPrime does. And we just pass that in as a function, and that's then used together with the Memoizer that we looked at before in order to only call the isPrime check if we don't find the key or the prime candidate in the map that's passed to the Memoizer. So let's go ahead and take a look at time test. Time test comes here, takes in a Memoizer and a name, and it runs the timer. You've seen this a million times before. A time run simply just goes ahead and starts the timer, takes the current nanotime, calls the method under test, calls stop timing, which records how long it took to execute, and then we stick that test name and that execution time into the results map, which will be used later to get the result back. So that's what time test does. Now let's go ahead and take a look at what it's timing. It's timing something called RunTest. So here is RunTest. So RunTest is going to run the prime number test using Java structured concurrency. Now we haven't spent a lot of time on Java structured concurrency in this class. It's covered in one of my other classes, but I thought it was kind of fun to show how it's used here. So basically what we do here is we start by printing out some diagnostic information. We set a counter back to 0 so we can keep track of how many prime checks occur, how many duplicates there are, for example. We then make ourselves a new array list of size elements, where size is the number of random integers we're dealing with. This is just to avoid having to reallocate that array. And this array list is going to be a list of futures to prime results, because that's what Java structured concurrency expects. It creates futures. So here's what structured concurrency looks like. It's kind of a cool approach. It has its pros and cons, but this is basically what it does. So we make ourselves a new structured task scope object, which will shut down if anything goes wrong. That's what shut down on failure means. So we have a new scope. And then for each of the random integer objects that we had created before, we print out a debugging message. And then we're going to go ahead and call the fork method on this structured task scope object. It's defined here in the try with resources block of the try finally block or try catch block. And fork goes ahead and creates a virtual thread to run this computation. So the virtual thread, as we've talked about before, doesn't consume much space. You can have thousands of these virtual threads running around. And what this particular virtual thread will do is it'll check to see if that random integer is prime using the Memoizer that's passed in. And what comes back from fork is a future to a prime result. So we are going to store that into the results list. So we have this list of futures to prime results. Now, after we've started all of those fork virtual threads to run those prime checks, we're then going to call the scope join method. And that's a barrier synchronizer that waits for all the thread objects to finish in this scope. That's what makes it structured concurrency. And if anything goes wrong, an exception is thrown. In this particular case, an exception will not be thrown, but if there is an exception thrown, we catch it and then rethrow it. So when we exit this scope, we know that all the virtual thread objects have finished. And so what we're going to do at that point is we're going to go through the list of futures to prime result objects. And for each of those futures, we're going to say, hey, get that result right now. There's a new method that was added in Java 19 or Java 20 called result now. And when you call that on a future and the future is known to be done, which it is in this case, that will return the value without having to deal with ugly checked exceptions. So we then call the handle result method, and the handle result method will then print some results out if we have turned debugging on, indicating whether the values are prime or not. The last thing we do is we print that we're leaving the test and say some things about what's going on, how many duplicates there were, and so on and so forth. And then they return the Memoizer that was updated during the test. So that's what that particular method does. That's what the the method does called RunTest. And you can see here when we're all done, we're going to print the timing results. And then the final thing we're going to do is we're going to print out the results. So we're going to give it the StampedLockHashMap, which we treat as a map. We're going to sort that map. We use this little utility implementation that's going to sort the elements in the list by the comparator. And then we're going to make a new linked hash map. We're going to store the entries in the hash map and return the hash map. We use a linked hash map, so the order of printing when it is iterated through will be in the order it was inserted, and it was sorted to begin with. Then what we do is we print out the primes and we print out the non-primes. Here's how we print the primes. We go through the sorted map, and as long as the value is equal to 0, meaning it was prime, then we keep going and add it to a list that we're going to print the primes out with. The second we hit something that's not 0, we know it's a non-prime, and so that's the smallest factor. And so we break out of the loop, we print out the primes. Here's what print non-primes does. It's basically the same idea, except in this case, we're going to use an iterator, and we're going to keep iterating and skipping over the primes. And when we find the first non-prime, we add it to the non-primes list, and then we break out of the iterator, and then we go through the rest of the elements in the iterator and add them to the non-primes list and print that out. So that's basically what the program does. Let's go take a look now and see what the results were that we got back here. And as you can see, we had a count of 200. So we had 200 random integers we wanted to check. As you can see from the diagnostics, 78 of those things were duplicates, which meant that we didn't have to keep running the isPrime method over and over and over again. We were able to look it up in the map. And you can see that we ended up running each of the different Memoizers, SynchronizedHashMap, ConcurrentHashMap, and StampedLockHashMap Memoizer. And then we took the results and we sorted them from fastest to slowest. And as we would probably expect, the ConcurrentHashMap was really fast, and that's because it doesn't do locking of the entire data structure. It just has locks on each of the hash table buckets. So there's very little contention. So you can see it's substantially faster, like 4 times faster or so than the other approaches. StampedLockHashMap Memoizer is a little teeny weeny bit faster than SynchronizedHashMap Memoizer, but not by a heck of a lot. And that's largely because we used the version that was the optimistic lock mechanism. And in this case, we're having a lot of contention because we have a lot of threads running. We've got basically 200 virtual threads all running. And so that's a lot of contention for that stamped lock. So the optimistic locking mechanism didn't really bias very much. In fact, none of the mechanisms are going to bias very much because there's a lot of contention. If there were not much contention, then we would expect to get a bigger win with the StampedLockHashMap Memoizer. As you can see, when we're done, it goes ahead and sorts all the results and prints them. You can see that there were a bunch of primes. There were 1, 2, 3, 4, 5, 6, 7 primes, I believe, and then a whole slew of non-primes. And this tells the non-primes and their factors as well. So that's basically what that program does. It's really cool, shows off a whole bunch of interesting things, including Java structured concurrency, stamped lock, the StampedLockHashMap. And under the right circumstances, we could expect to get better results from stamped lock. But because of the way we ran the test program and the number of threads that we had going and the contention on that stamped lock, we really didn't see a big win relative to just using the synchronized hash map. And of course, the synchronized hash map uses a single lock for the entire hash map. So it's about the most contention you can imagine because it's got locking everywhere. So that's the end of this particular case study.